Oh, lighting.
Different, yeah, different. What's it like? Materials.
Yeah.
Diffuse materials and a bunch of explaining of physics and stuff.
Yeah. Okay.
Physics.
No, there.
Okay. So we have diffuse material. What was that doing? Diffuse. Hang me. What's the idea about diffusion or yeah?
Different dispersion of light in on the materials.
Yeah.
Ray tracing.
Yeah. Cool.
What was the other one?
We had path something, not pathfinding, but
Path tracing.
Yeah.
path tracing.
Yeah.
And
What
Ray
was
tracing,
more
path
that
tracing.
was better for?
yeah, the cooler ray tracing. What was that?
That was path tracing.
That was path tracing.
So what was the opposite of ray tracing? Ish?
Something else.
Yes.
Photon mapping.
Ah, there you go.
Photon mapping. That was
Yes.
that was the cooler ray tracing.
That's the cooler
No,
ray
that's
tracing.
the path tracing.
Yeah. So exactly, the cooler ray tracing is path tracing, and photo mapping is the opposite of ray tracing. So that's roughly, I guess. Let's use that formula to assess what we talked about.
If we write that on the exam, that's
Exactly.
like 10 out of 10.
Well, it says it definitely shows that you have conceptually understood the differences. It doesn't necessarily tell me if you understood the concepts by themselves, right? So, which is a quality criterion we accept, I guess, to some extent. You won't get full marks, but yeah,
You might get 1 or 2.
may get something. Cool. What else did we talk about? So this was, if we put all those concepts you just talked about, which category do they fall into? Or
I mean, the path tracing is called luminosity methods.
Yeah.
The other ones were just like light. I don't know what category does that go in.
good.
Local luminosity methods.
Okay. Which ones are you referring to?
The ray tracing and photon mapping. I mean, are those just local then, if the path tracing is global?
Okay. So, okay, clearly, nearly. So the idea was that all those concepts were among the global illumination models, right? Because they model the entire scene. The ones that were probably more, the differentiating criterion was a different one. Question is, can we use any of those for games?
No, they're too slow.
They're too slow, right? So they're by a factor 1,000 too slow, right? So it's probably, well, you know, we're getting better performance nowadays. So ray tracing is coming into the range of the possible, but still realistically, we need to use other approximations. And probably, if anyone can lower a light, would be great. So all those global illumination models are somewhat approximation of what?
Just photons, light.
Yeah. And in terms of graphics, we talk about one concept which are all, you know, are built against. Which you're right. You're looking for the physical representation of the world, right? So, but we had a theoretical representation of the physical representation of the world that we approximate towards in graphics, right? No, too much.
Too many layers.
Yeah, which was that called? How was it called?
Never go to
Equation, something.
Yeah, exactly. That was the subset of that one. The something. The other one was actually quite straightforward. I'll bring it back up because it's so super ugly.
Rendering equation.
Sorry?
Rendering equation.
That's right. Exactly. So let's bring it back up so we don't confuse the one. That one, right? Super handy. We talked about it. And this is basically, if we manage to represent this one, we kind of have a sufficiently, you know, accurate representation of the physical environment. Any objections from professionals? No? So right, this is what everything builds against, right? So, and then we talked about the individual components, emitting light, then reflection components, and incident angles, and so on. We're not repeating all that one, but this is the idea that all those global illumination methods approximate somewhat of what's happening here in a better or worse fashion with better performance and, you know, sacrifices on in terms of accuracy and features and so on. But so the question was then, how do we do it in computers? And that's where we ended up. That's why I want to get back there. So how can, because all of those were too slow, right? So for games, how can we do it in games? And for our, you know, starting purposes. Of course, there are more refined mechanisms, but what's the model that we talked about that we can actually use in practice? That's where I lost all people. Yep, okay, cool. Lecture was too long on Friday. Now I know. Anyone? Starts with a P.
Pre-compute.
Okay.
Pre-render.
Okay. So no one was here. Okay, that's cool. No one really?
Probability.
Pi.
Okay. Yeah, you're daring. Okay, right. Okay, let's ignore all those. Spend too much time on those, apparently. But what I want to get at is this thing, the Phong model, Phong reflection model.
Ah.
Yeah, somewhere there. After a break. Note to self: never do breaks again. They all drift off after. Just kidding. So Phong model. Right. And the idea is that is a kind of a simplified, the simplest way of doing lighting, right? So in a generalizable fashion. Of course, it's not accurate. It doesn't have all the features and the physical accuracy that we have in, photon mapping or ray tracing and so on, which actually try to represent physical phenomena. But here it's like, how can we emulate the reflection or the lighting characteristics so that it looks like as if there was really some sort of lighting in the scene? Because, it's not like we have a 3D scene with dedicated lights set up. We need to emulate how an object would look if it had proper lighting in the scene, right? So, and that's the precise idea of this Phong model, how we can take shortcuts wherever we can, and the biggest shortcut is on the left, and it becomes a bit more moderate to the right. So the first component was ambient lighting. What was the idea about ambient lighting? Where are you? Okay. First unit. Sorry.
Oh yeah, me first. It's the
Sorry for that.
bare minimum like color value any pixel can have on an object, so that you can't just have something that's completely pitch black.
Cool. Yeah. Yeah. Now, Ed, anything to contribute? Sorry.
No, I think it was.
Yeah. Cool. God, guys, I need to have a bit peripheral vision here. Since you are talking all the time, so what about you? So
It's a very cheap method to basically do reflected lighting without actually doing that. So you, instead of just having a pitch black corner or something, you just have a passive lighting.
Yeah. So I think I am to the way I understand your comment is that you emulate as if you are in a 3D space with reflections from the walls, even though you actually physically don't have any of that, right? So you assume a base level of lighting, like in this room, that we get by having something here without any direct illumination from the projector or the sun or any other directional source, right? So yeah, that's right. So it's a cheap hack, yeah, but it's a good cheap hack, right? So okay, that's the base lighting. But again, we don't have any directionality element here. So meaning it looks like 2D, right? So we don't actually see any depth element, depth component here. The second one was the diffuse lighting. What idea was the did we have here? What was the diffuse lighting intuition?
Takes into consideration the direction of the light.
Cool.
So that's the whole amazing formula on the previous slide.
Yeah. So yeah, there's the what BDRF bidirectional reflectance, distribution function. That was the one, right?
Sure.
Something like that.
Sure, of course.
Sure.
Cool. Yes. Very good. Okay. I get also 1 or 2 points in the exam. That's pretty good. Anyway, here's the diffusion idea is there, that we have a surface, right? But the surface is not entirely flat, right? So it's like rugged whatever else, and it may also be tilted towards a given direction, right? So if I'm, for example, looking at the projector and I'm facing it directly, I have the possibly highest illumination. If I face sidewards from it, then obviously the illumination decays. So, and that is somewhat reflected in the idea of diffusion, but it obviously has the directional element, but also the material component, meaning if the surface is actually flat or rugged to some extent, because in a perfect reflection model we would have the idealized optical reflection idea, or in a less optimal model, or in a perhaps more realistic but less physically accurate model, we probably would have something like that in a much more random distribution. seemingly random distribution of reflections. So that's the diffusion model. So it's basically taking directionality into account. And that fellow here, what's that doing?
You could say that it takes the camera into perspective because it bounces off the object and then into the eye, sort of the person or the camera. So
that's right. So it's pretty much exactly what you said. It's reflecting the idea that we have a perspective on the item, and it basically takes a subset of the angular simulated rays that are actually bouncing off the material that actually hit the camera or your eye, if you like, right? So, and then you have the specular effect, which is basically just, you know, white light, right? So that's like the highest possible illumination. If you put all that together, you hopefully have something like this, which looks pretty cool, but it's actually just in a head, right? So it didn't really resemble all the characteristics that we had in the other global illumination methods, like modeling rays or photons or anything fancy like that, or even proper reflection from walls or the like. But it's just approximating this on the object. So that's the idea. Cool. One of the concepts that we talked about was the normal. What is the normal? Briefly talked about it. Yeah, exactly, that thing. I'm not sure how you write that in the exam, but it's pretty much that thing, right? If you take a shot with your smartphone, you attach it to the exam, you probably pass. So, yeah, so perpendicular to the surface, right? So, that's right. So, and we use that for calculating the angles of reflection and the like. We'll come back to that again and again. So, let me go skip all that because I actually wanted to end up here. That's more realistic. So, and if we add all those components together, we kind of arrive at the ultimate color for each individual pixel, ideally, right? So if we consider all those aspects, other aspects we need to consider are attenuation, which is like the distance from the light. We didn't talk about this yet, but we need to model somehow the decay of luminosity based on the distance from the light source, right? And potentially gamma correction. So yeah. Which is a hardware problem, or let's say a more physical problem of the devices we're using for representation. Yeah, I put this under optional, but we'll get there. So I mentioned that this is the outdated code, we're not using that. So let's look into individual components and see how we can apply them in the context of OpenGL. The obvious one is ambient lighting. If we have, for example, an initial color of an object at a given vertex, and we apply the ambient light that we have in the environment to it, we get the final color, right? So no surprises there. I think that should be relatively straightforward. Any disagreements? Kind of works, right? So that's the easy one. The biggest head, yes, yet the easiest one to model. And the other one, that's diffuse lighting. So the idea here is that this is kind of the base model of doing a reflection on a material. Of course, you couldn't consider other material components that are relevant here. We ignore them completely. So instead, what we're modeling is the direction to the light source. Then, yeah, we normalize that direction, normalize that vector, so we can actually use it for calculation afterwards. Then we calculate the diffusion vector, which is basically just the, hang on, there you go. Here's the, let's say that's the light source, here's the normal, and we kind of need to figure out that thing here. And I always found I use theta in order to represent this. So we need to find out that angle. And we do this using the dot product of the normalized vector to a light source and the normal of the object we're dealing with. And we need to ensure that it's greater than 0. Otherwise, it's we shouldn't have any diffusion anymore because it must be behind the. It will not have any sort of illumination anymore. So if we have a difference between the normal and the light source, meaning I'm pointing at the light source, my normal is facing the same direction. I have an angle of 0 degrees, right? So I get the full illumination, right? So the diffuse factor will be 1. And the further I move away with this, the greater the angle becomes, and the smaller this diffuse factor will become. So the light that's coming from the projector towards me right now will decay. So if we use then that diffuse factor and multiply it with material color, that's the input color of the material, whatever that was, blue in our previous case, and intensity, then we ultimately arrive at the diffusion color. There's obviously here's opportunity for modeling materials much more accurately as we do, right? So that's a very simplistic approach towards modeling material characteristics, but that would be a possible way of putting other components into it. We talked about some material characteristics, which were? Yes, exactly. Look back. That's brilliant.
Translucent, reflective, diffuse, or absorbent.
Ah, brilliant, right? So cool. We had the idea. Okay, how reflective is material? How much absorbing is it? Black, for example, absorbs matte black would absorb the color. What was the other one? Transmissive, right?
Translucent.
Translucent. Okay. And
how? So you have. I mean, that's.
Yep.
I don't even know if that's the proper word to use for it. That's just what I wrote down. But say you have, for example, a glass of water.
Yep.
It breaks the light and I don't know, transforms it, and I don't know.
How do we call that?
Bends it.
The bending thing. How did we call that one? The particular to the glass of water thing. What was the term for that one?
Refraction.
Refraction, right? So, and there was the other thing that is also about transmission into material that has some characteristics that happen in the material. What was that one? Stuff that happens here, right? So something penetrates the material, and then some reflections or
scattering.
Sorry?
Subsurface scattering.
Precisely, that's the one, right? Subsurface scattering. So we have this effect of illumination and so on, and it reacts depending on the density of the material. So that's the more complex one. I'm not sure if we get perhaps a talk by Ahmed at some stage about subsurface scattering, or is that not something?
Probably there are other researchers as well who are working on this.
Agreed. So that's definitely much more focused on the material representation, then materials become much more relevant, way more than we have it here right now, right? So we're assuming an opaque surface in this particular case. Okay, yeah, last one is the idea of having specular lighting. So we need to identify, okay, from the incoming light, or given the incoming light and the normal of the surface, we need to model the reflecting vector in the first place. But then the critical thing is to figure out, let's assume this is the reflection vector here. Reflection. Right. But the camera is somewhat here, right? So we actually need to figure out what the difference between those two ones is, right? Because depending on that vector, depending on that angle, let's call it gamma for now, it will determine how far there will be specular effects, right, on the material, right? So if it's aligned, if the reflection is aligned with the camera angle, then we probably have, a large specular area on the material. And if it's with increasing size of this gamma right now, it will be smaller, right? This specular effect. And that's precisely what we're modeling here. So, to model the incidence vector, we have the surface to light. We do reflection. Reflection, this function is built into GLSL, there you go. The GL shader language, right? So we can directly use it. And uses the normal of the surface as input. And as a third element, we calculate the direction towards the camera. And then we determine the cosinus of the angle of this vector and this vector, the reflection. And that basically gives us the basis to calculate some sort of specular coefficient that we determine ourselves. This parameter allows us to indicate how wide, how intense the specular effect will be. So the higher the value, the narrower the angle will be in which the specular effect works. But if you reduce it relatively, then you have a wider range of specular effects on the object. So that's the rough component here. Input is the material, the base color of the material, the specular coefficient right now, again, the offset of the size of that angle determines the extent of the specular effects and the lighting intensity. So that's one of the aspects. One practical aspect here is if you don't have any diffusive effect on the material because it's not, it's not illuminated by directional light, you don't need to bother calculating that stuff in the first place, right? So it's a good way of determining whether you actually need to worry about specular effects. If you don't have any diffusion on a particular pixel or and so on, then you will also not have any specular effects on it. Let's see. Thoughts, questions, worries? Certainly not the only way of doing it, but that should be the intuition. Does it somewhat make sense? Yeah, input angle, reflective angle, and difference between camera and reflection angle will determine the level of shininess. And you parameterize it as much or as little as you want. The last thing is, oh no, not quite the last thing, the second last thing, attenuation. That is the loss of light over distance. So the idea is that light intensity decays over distance, and we kind of need, or you may want to model that as well, right? So if you have a particular position that is further away from the light source or closer, you can model simply that decay. And to model it, one possible approach is to use some sort of attenuation as a factor of retained light. So the light that you actually retain after over given distance, we can calculate it this way here. And if you want to, so idealize, it would be directly 1 divided by the distance to the power of 2. And if you want to control the attenuation, because, I don't know, for whatever reason you want to control the brightness levels or have varying brightness levels for objects that have a relationship to the distance, but you want to control the extent of the decay, then you can also introduce some factors to do that. Cool, so that pretty much should give you the final color. Again, the important thing is that the decay of the loss of light over distance will only apply to the 2 components of the Phong model that are actually directional, or that have directional components, which is the diffusion idea and the specular component, not the ambient component, right? So the ambient component doesn't have directional component, it's just the base light, it's the ugliest and dirtiest heck we have there. So, and this is not even reflecting decay of light. And then last but not least is possible gamma correction. So, and it really depends what kind of material you're, what kind of input you're dealing with. The idea is there that the human eye has a very different perception of brightness in particular compared to the, a accurate objectified representation in hardware devices. And the idea is that if you have an input like this, a linear encoding would correspond to that representation here, but it turns out the human eye is very, very much more receptive towards low light conditions for, I think, survival reasons, let's say. For example, at night you're probably much more likely to spot your predator if you are sensitive to nuanced lightless levels in low light. And this human characteristic gives us a bit of a biased perception of brightness, and this needs to be accommodated in the otherwise linear representation of brightness in monitors, LCDs, projectors, and so on. So depending on whatever input resource you get, for example, textures, or if you don't use textures but directly model color in vertices, you need to accommodate the correction for that one. So in this case, you would need to in this particular case, you would need to apply this function to correct for a gamma value of 2.2, which seems to be standardized across display devices, right? You guys do color stuff here? No? Yes? You are acquainted with the details of that?
Normally, gamma correction is usually for just contrast.
Mm-hmm.
So you can, anyway, you can also try it with simple script in Python to apply gamma correction, see how you can modify the contrast of your image. So it's about perception make it human visible much more.
So yeah. So so the messy bit here is, in terms of the application here, it depends what input you have, whether you need to apply it or not, because some textures have this correction included already for the output device bias. And some don't. So if you model color from scratch, as we did right now conceptually here, you would need to apply the gamma correction to have an accurate perception of brightness that corresponds to our unit perception. Yeah, so that's the magic here. Again, if the textures you're using are already encoded, that's why you don't need to do that. That's the key idea. Thoughts, questions, worries? Yes, of course.
Can you explain what sRGB spectrum is?
The SRD is a standardized format by industry, a consortium like Microsoft. Who else is in that one? You know? Sorry?
Adobe software.
Adobe, yes.
They also have this, when you save your image, for example, they have this option of sRGB. So it has, like, for example, at the display brightness, at what condition you have to see it. There is a lot of standards with sRGB. So like illuminant condition and a lot of things. So it's about how you view the RGB. So based on that one, they standardize.
So a lot of meta information beyond the RGB that we are intuitively dealing with, right? So that has more device dependent or device specific components and works across devices as well. So matter of standardization. Thank you. Yeah. So that's one of the aspects there. Cool. So yeah. So if you need to do it the other way,
but what exactly is the difference?
The difference is you're correcting for, so this is the idea of how the using the conventional algebra that we use here, we would end up having a linear representation of brightness, right? Because we always, the only thing that we're doing is having a base color material, and we're increasing or reducing the brightness.
So in practice, you just have to know whether the texture you have has already had this done to it, so
yes,
you can't do it twice.
That was what I was trying to say for the 5 minutes. Yeah, I don't know. Sorry, I failed. But that's precisely it. So this is the linear representation, and we just need to accommodate that the human eye's perception is slightly different, right? But the point is that oftentimes it seems to be more subjective than anything else. So you look at the output and say, hang on, there's a bit, you know, the darkness differentiation is really moderate. Most likely, you may want to apply this gamma correction, see if you have a more nuanced representation of dark shades or corners or whatever else, right? So in your model. So that's the idea there. But yes, that's precisely it.
And that's a sentence. Why do you use 5 minutes on it?
Well, you know, to motivate it. But I may have failed. So. Last aspect, what's the difference between those two ones?
Tessellation.
Okay. What else? Oh, other views? It's a bit blurry because I was doing some dodgy last-minute stretching. Not zooming, basically, yeah.
It seems the flat shading is only calculating based on the polygon it's reflecting off, while the font shading is using sort of making it rounder.
Yeah, okay. So does anyone want to refine that comment, because it's kind of nearly super spot on? Is it the same kind of functionality or not? Is it fundamentally different? What's happening here?
I mean, it's the same geometry and it's the same lighting conditions. It's just
but the flat shading kind of treats it like a bunch of flat planes.
Yep.
More or less.
Yep, that's right. The key difference. Anyone else?
Oh, I remember this actually from earlier.
Did we talk about it?
I didn't write it down.
Did we talk about it? No.
Earlier when.
Yeah, I alluded to it probably.
Earlier.
Implicitly, yeah, that's right. So the idea is that fundamentally doing the same thing, right? So we have the Phong model here, but I can say, hang on, this thing is actually only modeling, polygons, right? Or quarks or whatever that would be. Point is, the idea here, this is the fast version of that one. So the idea is that this is modeling based on vertices, and this is modeling based on pixels. So if you apply Phong shading, for example, in the vertex shader, the idea is here you take the 4 vertices, calculate the lighting conditions for those ones, and then interpolate between those ones, and then you apply it to that entire geometric primitive that you associated, that you know drawing here, basically, right? Okay. So that's the key idea here. This one here is done in a fragment shader, so it works on pixel level. It does it for everything, for every individual pixel, and therefore you have this much more nuanced, refined perception. So you don't see those weird, this segregated artifacts really. It's quite well modeled within the particular vertex, but you see the boundaries very crisp and sharply because they use the next adjacent 4 vertices and interpolate between them. So which one is faster?
Left.
Of course, right? So way faster. So this is kind of the fast version of, if you need to do calculate lighting conditions fast and you don't have much memory or whatever else, you can do it using the vertex shading mechanism.
So the left picture is that, the right picture is that a result of some processing of the first picture or the first model?
No.
Or is that 2 different results from 2 different techniques?
That is 2 different sides from different techniques, because we have interpolation here, which is not something that happens here, right? We work on pixel level, individual pixels, but here's some further functionality involved to establish that one.
So it's not just different steps in the same pipeline?
No,
Okay.
it's different, yes. But this fundamentally, that's the cheap version. It's called, what's the name for that one? Giro, the Giro model, or Guro shading, right? So I think so. So anyway, that's the flat shading variant. The idea is they are super for low-performing graphics, hardware, whatever else. That's a good alternative to doing the very same thing, but using it, approximating it somewhat. Please.
It's also a distinct style of rendering, which, even though you have enough performance, you might go for the left one because you want to just adhere to that style.
Yeah.
Like low poly,
flat color games.
Of course.
like Minecraft.
Of course.
Like where you don't care that it's so.
Yep.
There's many games like that. Totally new games. Just.
Yeah. So yeah. Games is obviously.
And somehow they still make them run like shit.
Sorry.
And somehow they make this low poly, flat color game still run like shit. I have no idea.
We just don't know how to optimize that.
Anyway, so but just if you come across that one, it's called flat shading. So it's basically a halfway approach. But the original idea was to increase performance here, whatever the stylistic implications may be. Nowadays, is a different story there. But just also for you to bear in mind, you could actually take shortcuts here and there. Cool. That was all I wanted to say about OpenGL and lighting. So we take everything that you learn in the theory, or we talk about in the theory bit, right? So you kind of can forget about it because that is not relevant for the foreseeable future, at least the next 5 or 10 years, until it actually can be done in real time, right? Of course, for offline rendering, you can use most of those mechanisms, but it will take some time until ray tracing actually becomes real-time capable, I guess. Or is there any evidence that it's already usable?
I think with Monte Carlo simulation, you can parallelize the easily.
Right.
They can support a lot of multi-threading to sample to do the ray tracing, and then you can have realistic with few iterations.
Okay.
So
Is it real time?
It depends on the computing power you're using, but yeah.
Yes. Okay. So there, we're getting there, but I don't think it's yet reality, right? So in a typical 3D title as of now, you probably would still find it yet. Cool. Yeah, that was everything I had to say about lighting. Slides on the in the wiki, or link from the wiki anyway. Any questions as of now regarding lighting or darkness? Oh no, darkness later. We didn't talk about shadows yet. So okay, everyone somewhat locally illuminated, yeah? Okay, all right.
How are you going to deal with encoding the normals into the texture? Like having normal maps? Or how are we getting the normal information? Are we just hard coding it?
The normal information would be the can't we derive it from the geometric primitive we're modeling? So it needs to be perpendicular to the surface, right?
So you can just compute it.
That's right. Yeah. So we don't dedicate because that's cheap from a shader perspective.
Yeah.
So yeah, you just rely on the geometric shape that you're actually modeling and then calculate the normal ad hoc. So.
Can you have like inverted normals in OpenGL so that you have them inwards into the object rather than outwards, or will it just check that it is perpendicular?
Yeah, you have an invert function in GLSL. Yes, you could do that.
Yeah, but I'm thinking like, would that so it does change how it works, right?
Yes.
The result, okay.
Yes. Yes.
So you need to make sure that they are in the right direction,
Yeah.
not just perpendicular to it.
That's right. Yes, you need to. Direction is important. I mean, that's the key purpose. They point. The normal is indicating direction, nothing else.
Yeah,
right?
like it indicates direction upwards. I'm thinking like if it's pointing downwards, then it would try to make the light get in there and then into the object rather than out.
Right.
So is that something?
Right, but okay. Well,
Well, they just render black.
it should just render black because we're modeling only opaque surfaces for now. So we're assuming that the surface is non-light transmissive. So yeah, it would render it black. If the case was that the light is behind the surface, then yeah, you wouldn't see anything. It would just be black. We do some of those components in Lab 6 anyway, right? So playing around with this.
We can
But-
also do cross products.
Yeah.
Because the cross product of two vectors is perpendicular to the surface. So you can get the normals like that.
Ah, right. Okay. Cool. All right, I'll leave it at that because that was Friday material. What I would like to, hang on, what's the time right now? Oh God. All right, you get your, who usually wants breaks here? Anyway, so you get your, what do we say, 10 minutes breaks if you have to, or 5 minutes if you prefer to. Hint. 10? Okay, or whatever.
30.
So, okay, so you don't, please, as long as you come back. So, 5 minutes after 1. The ones that want to, or that I encourage you to talk, please come a bit earlier and you can set up your machines. So you can show others the code and we can comment on that. So you have 5 minutes break, and at 1 you probably want to start lining up and setting up your machines.
You are game proficient. Yes.
I will restart the stream once the other machines are set up.
Help. Update wall.